Building has 5 alarms configured in such a way that the system functions if at least 2 of the alarms work. So that's if at least 2 of those alarms work, the system's going to work. The probability that an alarm fails overnight is 0.05. Let the random variable x denote the number of alarms that fail overnight. And remember, there's 5 alarms. So this looks to me very much like a binomial distribution. So we've got a fixed number of trials, which is our 5 alarms, and the probability of failure is a constant 0.05. What assumptions are required for the distribution in part A to be valid? So let's think about the typical things for the binomial. So alarms independent. In other words, that one alarm failing doesn't have a negative impact or even a positive impact on the other alarms, so they're independent, and that we have a constant probability of success. And that ought to do it. We know we've got a fixed number of trials because we only have the 5 alarms. What is the probability that the alarm system fails overnight? Well, in order for it to fail, remember, it'll work if we've got 2 alarms working. We need 4 or 5 of the alarms to fail. So we're after the probability of x being greater than or equal to 4. And we should be able to do that straight on the calculator. So we've got binomial CDF, 4, 5, we know the number of trials is 5, and 0.05. So that is 3 times 10 to the negative 5, 0.00003. One of the alarms is removed in the evening for maintenance and is not replaced. What is the probability the alarm system still works in the morning? So now we've got a different binomial with 4 alarms, and let's assume the probability is the same since we're told nothing different. So this time we're going to need 3 or more to fail. So that's going to be a binomial CDF, 3 to 4, with 4 trials, 0.05, and that gives us 0.00048. So that's for fail, and we want the probability it still works in the morning, so it's just going to be 1 take away the failure. That will just be 1 take away my last answer, which is 0.9995.